In the previous lecture, I did a full one-way ANOVA, and now we're going to do a post-hoc test for that ANOVA. So remember that after rejecting the null hypothesis in an ANOVA, all you know is that the groups you compared are different in some way. Like here is the example that I did a few lectures ago. I had researchers who wanted to test a new anti-anxiety medication. So we had three groups, 0, 50, and 100, and we measured anxiety scores. So we were going to test the hypothesis that not all means were equal. We tested to see if there was a difference somewhere between 0, 50, and 100, between those three groups. And we ended up finding out that that was true. We did our ANOVA, we rejected the null hypothesis, and we found out that, okay, the groups are different. Our alternative is true. So now that we've rejected the null hypothesis, it's appropriate for us to perform a post-hoc test. This post-hoc test is going to tell us where the groups are different. Maybe all three are different, maybe only 0 is different from 50, or 0 is different from 100, or something like that. We can ascertain exactly where the difference is. Now there are a bunch of different post-hoc tests that we can do. I'm going to show you two of the most popular ones. We're going to do a Tukey test and a Scheffé test. Now, the Tukey test is more liberal than the Scheffé test. What that means is, when you perform a Tukey test, you have a greater chance of rejecting the null hypothesis, but you also have a greater chance of making a type 1 error. With the Scheffé test, you have less chance of rejecting the null hypothesis, but you also have less chance of making an error. So Tukey, you might find what you want, but there's a bigger chance you'll make a mistake. And Scheffé, there's a smaller chance you'll find what you want, but there's also a smaller chance you'll make a mistake. That's what that means. So the Tukey HSD means honestly significant difference. Now with this test, we're interested in examining mean differences. So these are our three groups, 0, 50, and 100. What we're going to do is we're going to calculate the mean for each group. So the mean for the 0 milligram group is 8.14. For the 50 milligram is 6.71, and for the 100 milligram is 3. That's just mean. We already know how to do that. That's pretty easy. So now we're just going to deal with these three means, and we're going to calculate this Tukey HSD statistic using MS within from the table before, N, and this new statistic, Q. So here's our table. We're going to use our MS within. Just put that right in there, 0.57. And N was 7 because we had 7 people in each of our groups. That's stuff that we already know. We just need to find Q now. In order to find Q, we have this special table, the Q table, really. Now we know that we have 3 groups that we're comparing with 18 degrees of freedom. Now using alpha 0.05, which we usually do, we find a Q value of 3.61. So that's the Q that we're going to plug into our equation. Remember, we find this Q using the number of groups we have, our degrees of freedom, and our alpha. So it's the stuff you already know from the ANOVA that you did before. So now we put in this 3.61 and find an HSD of 1.03. So what that means is that any two means that are more than 1.03 apart are significantly different. So down here you can see I'm making 3 comparisons. 0 and 50 are 1.43 away from each other, so that means they're different because it's greater than 1.03. 0 and 100 is 5.14 away from each other, so that's different. And 50 and 100 is 3.71 away from each other, so that's different. So all 3 of these groups are different from each other using the Tukey HSD post-hoc test. Now next we have the Scheffé test, where we're going to calculate an F statistic just like the ANOVA from MS between divided by MS within. Now the MS within is going to be the same thing as in the ANOVA. It's going to be 0.57, but the MS between is going to be a little bit different. So here's our data, and here's the equation for MS between. Now Scheffé is a pairwise test, so we're going to have to calculate 3 SS betweens, where we have 3 comparisons we can make. 0 to 50, 0 to 100, and 50 to 100. That compares each group to every other group. So let's say we're comparing 0 and 50. This is how we would calculate the sum of squares between for that. We take the sum for 0 squared plus the sum for 50 squared. divided by n, and then minus t squared minus n. T squared divided by n. This is all stuff we already know from the ANOVA, so I'm trying to move quickly. It's more of a review than anything else. But that's how you compare 0 and 50. And then you do it again. Oh, sorry, no, I'm skipping ahead there. You get the MS between, 3.57. And then you'd calculate your F for that comparison, 6.26. Now, you're going to use the same critical value that you did in your ANOVA. Our critical value was 3.5546, so our decision rule was, if our F was greater than 3.5546, we can reject the null hypothesis. And because our F was 6.26, we can reject the null hypothesis and say that the 0 and 50 milligram groups are different from one another. Now that's one of the tests, that's comparing 0 and 50. Now using this, try to do this on your own. Try to compare 0 and 100, and try to compare 50 and 100. Those are two more comparisons that you could do using the Scheffé test. And those are two different post hoc tests that are usually done after a one-way ANOVA.